everybody. This is our first video on section 4.2, the mean value theorem. So in this video, we're going to introduce Rolle's theorem and we're going to look at what it means and we're going to look at the proof of this theorem. Okay, so let's go ahead and start by looking at what Rolle's theorem says. Okay, so we are going to look at a function f. Okay, and we have f satisfying three different criterion. Okay, so f is going to be continuous on the closed interval, okay, the next criteria is that f is differentiable on the open interval, okay, and then the last criteria is that the function values at the endpoints are equal. Okay, so if we meet these three criteria, then what can we conclude? Okay, so we can conclude that there exists some x value c in the open interval such that the derivative at that value is 0. Okay, and this is what Rolle's theorem is. Okay, so we have to check these three criteria. It's continuous on the closed interval, it's differentiable on the open interval, the endpoints have equal y values, okay, and then we can conclude that at some point in that open interval, the derivative is 0. Okay. Now, before we look at the proof for this, I want to go over what we're going to need to remember for the proof. Okay, we're going to need to remember two different theorems that we went over last time. Okay, one of them was called the extreme value theorem. Okay, and if you remember, this tells us if f is continuous on the closed interval, okay, then f attains both an absolute maximum and an absolute minimum on that interval. The other theorem that we're going to need to remember was Fermat's theorem. Okay, so remember for Fermat's theorem, we know that f has a local maximum or a local minimum. at x equals c, okay, and f prime of c exists, right? This is another way of saying that f is differentiable at c, okay? Then the derivative must be 0 at c. Okay. So those are the two theorems that we're going to need to use during the proof of Rolle's theorem. Okay. So let's go ahead and look at the proof for Rolle's theorem. Okay. We're going to prove it using 3 different cases. Okay, and after each one, we'll kind of talk about graphically what's going on in that case. Okay. So let's look at the first case. Now, in this first case, we know that the 2 endpoints are equal, but it's possible that this function is just a constant function. Okay. If that's the case, right, and we know that everything is differentiable and continuous, okay, then we know for sure f prime of c equals 0, right? Because the derivative of a constant is always 0, right? And this is true for all c in the open interval AB. Okay? So if we have a constant function on that interval, then the derivative is 0 at every point in that interval, right? And that matches with what we want to conclude here. Okay? Now, if we are looking at graphically what that would mean, okay, we're looking at our 2 values, our interval A and B, okay? Our function is a constant, meaning it's a horizontal line, okay? And we can see that in any point on this horizontal line, the derivative is horizontal, right? The derivative is 0, the tangent line is horizontal, okay, for any point at that interval. Okay? So this is the graph of what this situation is describing. Okay, so let's look at a different situation where we maybe don't have a constant function. Okay, now in this example, okay, we're going to have that for some value, right, this value is larger than the endpoints. Okay, so for some value in this interval, the y value is larger than the y value of the endpoints. Okay, so we also know from our first hypothesis, right, that f is continuous on the closed interval AB. Okay, so this is the only condition for the extreme value theorem, is that the function is continuous. So we can apply the extreme value theorem. Okay. And in this case, we can conclude that f has a maximum, right? An absolute maximum okay. Okay, in the interval AB. Okay, now, since f of w is larger than f of a, we know that the absolute maximum cannot be the endpoints. Okay? Right? Remember, f of a and f of b are equal. Okay? So since f of w is larger than the endpoints, okay, the absolute maximum is not at the endpoint. Okay? So we can say it has to be at some other point. Okay? A point in the open interval, because we know it's not at A and it's not at B, right? We already know there's some point that's higher up or greater than the endpoints. So this absolute maximum is in the interior of the interval. It is not at the endpoints. Okay? We would say that this point is also a local maximum. Okay? If it is the highest point on the whole interval, it must also be the highest point nearby. Okay? We also know that by 2, right, our second hypothesis, f is differentiable. On the whole open interval, okay, specifically, okay, at C. So we know for sure that f prime of C exists. Okay, and what that tells us, right, we know that there's a local maximum at C. Okay, we know that f prime of C exists, so we know that we can apply Fermat's theorem. okay? And that's exactly what we want to conclude, right? That the derivative at that value c is 0. Okay, so let's take a look at what it's going on graphically. Okay, so again, we have our values a and b, okay, and we know that the y value at those 2 points is equal, right? Just like that. Okay, in this example, we're describing that there's a maximum on this interval, right? In the interior of the interval, meaning that there's some point that's higher than the end points, okay? Now, if we go up, we must connect this back down, okay? And we can see that when we do, there is this point here, this local maximum point, where we have a horizontal tangent, right? Where our derivative is 0. And this is our point C. Okay. All right. There is only one more case for the proof, so let's go ahead and look at case 3. Okay, so in this case, it's kind of the opposite of case 2. We're going to suppose that there's some w, so that f of w is less than f of a. Okay. Now, again, we are going to use the fact that the function is continuous we want to say specifically that it's continuous on AB, the closed interval. So we're going to use the extreme value again. All right, and this time we're going to focus on the absolute minimum. Okay. Now, just like last time, we need to know that the minimum is not at the end points. Well, it can't be, right? F of w is less than the end points. So maybe f of w is the minimum, but maybe there's an even lower point, okay? But the point is there has to be some point that is lower than the end points, okay? Okay, since we know that we have this point that's lower, the absolute minimum, it just can't be f of a and it can't be f of b because there is something lower than that on the graph, okay? So the absolute minimum has to be in that open interval. Okay. Since f of c is the absolute minimum, it is also a local minimum. Okay, and we know, right, that f is differentiable on AB. Right? So if it's differentiable on the entire interval, it must be differentiable at C. Right? F prime of C exists. That's what it means for f to be differentiable at C. Okay? So we know that f of C is a local minimum. We know that f prime of C exists. So we apply Fermat's theorem. Right? And that tells us that f prime of C equals 0. Okay? So what's going on graphically in this case? Well, again, we have our interval AB, and we know that our endpoints have equal y value, right? Now, we also know that at some point, right, the graph must go below that, right? It has to go down from those endpoints, okay? And if it goes down, you know it has to come back up to hit this point, okay? So when that happens, there is some point here where the tangent line is completely horizontal, right? Meaning that the derivative is 0. And this would be our point C. Okay. All right. So in the next video, we are going to talk about why it's so important to check the hypotheses or the conditions for this theorem. And then in the third video, we will talk about some examples of the type of problems you can expect to see with this theorem. Okay, I will see you guys then.